Let's take a look at some questions that deal with nuclear chemistry, which is chapter 5. So taking a look at question 5.56, it says determine the number of protons and the number of neutrons in each of the following. So the first isotope that I have is boron 10. So if I go over to the periodic table, I see that boron is element number 5, and the 5 is the atomic number, and that represents the number of protons in the molecule. And boron 10, the number 10, that identifies the mass number. So the mass number is the sum of the protons and the neutrons. So the number of protons, again, is governed by the atomic number, which is 5. And the number of neutrons is equal to the mass number. Subtract the atomic number. So the number of protons and neutrons subtract the number of protons. So I'm going to put 10 minus 5 here, and I get 5. So I have 5 protons and 5 neutrons. So let's take a look at the next one. So zinc 72, I go over to my periodic table. I see that zinc is element number 30, and my mass number is 72. So just like before, the atomic number represents the number of protons, so I put 30, and then the number of neutrons, I'm going to get that from taking my mass number, 72, which is the sum of protons and neutrons, subtracting the number of protons, I get 42. So there you go. I have 42 neutrons and 30 protons. In question 5.58, it says identify each of the following as alpha or beta decay, positron emission, or gamma emission. So in the first example, I have cesium 127, which is giving xenon 127, and this particle here. And this particle, if you've done any reading about nuclear chemistry, you'd recognize this as a positron, which is sometimes described as an electron with a positive charge. It's antimatter, so that's the positron. In B, I have strontium 90, which is producing yttrium 90, and this particle, so when I have this particle here, this is a beta particle. The beta particle. And then finally in C, I'll just use the black pen here. So I have astatine 218, which is decomposing into bismuth 214, and this particle here, and you might recognize this as an alpha particle. So this is an alpha particle. And an alpha particle is just a helium nucleus, and that's why we put the atomic symbol for helium, because a helium atom has 2 protons, 2 neutrons, and 2 electrons. But in the alpha particle, we've taken away the 2 electrons, so we're essentially just left with the helium nucleus. Also, I'd like to add that if you like to watch YouTube videos or read other chemistry textbooks other than the textbook for this class, sometimes you might see the alpha particle written like this, where they actually use the Greek letter alpha, and then they'll put the 4 and 2 like this. Similarly, sometimes you'll see the beta particle and the positron both written using the symbol beta instead of the E, and then they put the 0 and +1 for the positron and the 0 and -1. So just so you're aware of that in case you like to look at other sources. All right, the next question says, write the balanced nuclear equation for each of the following. So the first one is a beta decay of potassium 40. So I go over to my periodic table and I write down the atomic symbol for potassium. It's element number 19. The isotope is potassium 40, and it's undergoing beta decay. So I'm going to write down a beta particle. So let me just put my 0 here and E. There we go. And what I have to do is I have to make sure that the atomic numbers balance out on both sides and that the mass numbers balance out on both sides. So I can ask myself what plus 0 gives me 40, and the answer is 40. And then I can say what plus -1 gives me 19, and the answer is 20. So if I go over to my periodic table and look for element 20, I can see that it is calcium. So essentially, when an atom is undergoing beta decay, a neutron is becoming a proton. So you're increasing the atomic number by 1. The next one is with platinum. So I'll write the symbol for platinum, PT. So I look at my periodic table and I see that platinum is element number 78, and the isotope I'm dealing with is 190. It's undergoing alpha decay. So the first thing I'll do is I'll put my alpha particle down here. And I just have to ask myself, the same thing. I have to balance out the mass numbers and the atomic numbers, the totals on both sides of the equation, the reactants and the products. So on the reactant side, my mass number is 190. So far I have 4 on the product side, so what plus 4 will give me 190? The answer is 186 plus 4 will give you 190. What plus 2 will give you 78, and the answer is 76. I go over to the periodic table that I've printed out. I see the element number 76 is osmium, and there you go. I've represented alpha decay. So moving on from there. So it says, write the balanced nuclear equation for each of the following reactions. So the first one says, when two oxygen-16 atoms collide, one of the products is an alpha particle. So what I'm going to do is I'm going to write two oxygen-16 atoms. So I'll put one oxygen-16. Oxygen is element number 8. The second one here. And then one of the products is an alpha particle. So I'm going to put a 4 here and a 2. So this represents my alpha particle. So I have 16 plus 16 on my reactant side, so that would give me 32. So what plus 4 gives me 32? And the answer is 28. I have 8 plus 8 on my reactant side for my atomic number. That's a total of 16. I only have 2 on the product side. So what plus 2 will give me 16? And the answer is 14. So the answer is silicon 28. And the reason it's silicon is because if I look at the periodic table, silicon is element number 14. Oops. Moving on to the next one. Let's see. When californium-249 is bombarded by oxygen-18, a new element, seaborgium, which is named after Glenn Seaborg, it's a synthetic element. So seaborgium-263 and 4 neutrons are produced. So first I'm going to write down my californium, which is element number 98 on my periodic table. So it's californium-249. I'm going to add my oxygen-18. So I'm going to bombard it with oxygen-18. Oxygen is element number 8. So I'm going to end up producing 4 neutrons. So I can write 4 times a neutron, and the way you represent a neutron is a mass number of 1, but it's got no protons. It's just a neutron. So this dot represents multiplying. So that means there's a total of 4 neutrons. So if I balance that out, so if I have 4 in my mass number, and 249 plus 18 is 267. So if I subtract 4 from that, I get 263. And if I have 98 plus 8, that gives me 106. So if I go over to the periodic table, some periodic tables don't even have seaborgium on them, but seaborgium is represented by Sg like that. The next one is radon-222 is undergoing alpha decay. So let's write down the atomic symbol for radon, which is Rn. It's element number 86. I'll put 222 as my mass number for this isotope. I'm undergoing alpha decay, so I'm going to write my alpha particle first, and then I'm just going to balance the equation. What plus 222, what plus 4 gives me 222? The answer is 218. What plus 2 gives me 86? The answer is 84 plus 2 gives me 86. I go over to my periodic table. I see element 84 is polonium, P-O, polonium, like that. And the last question that I've chosen deals with half-lives. So it says, let's see here. It says, if the amount of a radioactive phosphorus-32 used to treat leukemia in a sample decreases from 1.2 milligrams to 0.30 milligrams in 28.6 days, what is the half-life of phosphorus-32? Well, the half-life is the amount of time it takes for a sample to decompose to half the original amount. So if I start out with 1.2 milligrams, hopefully, I think most people can just do this in their head. If I divide 1.2 in half, I'd end up with 0.60 milligrams. So that would be the first half-life. And if I divide 0.60 by 2, I end up with 0.30 milligrams. So this is what the question's asking. I'm going from 1.2 to 0.30. So this is my second half-life. So the answer is just that in the period, the total amount of time, 28.6 days, I underwent 2 half-lives. So if I divide that, oops, I'm supposed to say 2 half-lives. If I divide that number by 2, I end up with 14.3 days. So that is the amount of time it took for the original sample to decompose by half. I hope you find these questions and solutions helpful.